This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to continue the video on my spectroscope. So previously I showed you that I was able to assemble a spectroscope and make it work in a rudimentary way. So I calibrated it by using two lasers, and then I measured the wavelengths of different LEDs. But then I concluded that the construction that I was using was not really good in terms of like the mechanism, because the CCD was not precisely fitted in the casing of the optics, which is right here. So the problem was that I just put the CCD here, something like this. But yeah, you can see it's a wobbly thing, and then I could not put the top on of this optical arrangement. So then I decided to design another PCB, which is this guy here, which should be exactly fitting here. And as you can see, it fits here. So what I will do is that I will put together a circuit, and I will test this optical bench again, and then conclude how to proceed forward with this thing. And as you can see, we have many new stuff here, because this video is sponsored by PCBWay. Thank you very much for that. As you can see, I got this very nice clear PCBWay sign, so I will keep this here. And then I also got this ruler, which you can actually get by visiting their website, pcbway.com. And not only this kind of ruler, but all kinds of stuff, even this guy here, you can get it from their website. And obviously, which is more important, is that if you want to replicate these kind of PCBs that I make here, or you have your own PCB design, then you can very easily upload your Gerber file to their website, and then get your things produced by them, even assembled by them, for a very cheap price and for a very fast turnaround time. So please visit pcbway.com and have your stuff manufactured and assembled by them. So coming back to my design, the following thing will happen here. So if you remember, or if you have checked the previous video, then these were my PCBs. I just put this away because it's too shiny. So this was the previous PCB, and you can see that this is really shiny, but also it's large in size. And then this is the new PCB, and I will take several pictures of the new PCB, the bare board, and also the assembled board as well. And I will upload it to my website, so you will see it from close-up. But you can see the main difference is that PCBWay can actually produce two kind of black boards. One is a shiny black, and the other is the matte black. And for this task, I actually chose the matte black, and I guess you have already guessed why, because I did not want to have any kind of stray light and stray reflections inside this enclosure. So when this thing will be assembled, there will be very little amount of reflective things inside. Of course, we will have some exposed shiny metal parts, and we will have the legs of the circuit components, for example the shiny golden legs of the CCD. But at least I decreased the largest area which is there, because the largest reflective area is obviously not the pins here, but the board itself. And you can see that I hold them together so they get the light in the same way, and you can see the reflectivity of this guy. It's basically zero, so it's very good for this purpose. So also I have this nice stencil, as you can see, and actually I haven't modified the arrangement or the layout of the parts here, so I can also work on my old board, which is good for other purposes, because the old board has this very good hack that I have this STM32F401 microcontroller, and I designed this board with its circuitry that I can just plug it in. And then I have these 4 holes at the corners, and then I can just put it on an enclosure by using these 4 holes, or I can do anything with these. I can mount the circuit. And then here, of course, I just have the 2 holes, as you can see, because this guy here also has 1 hole here and another here. So this will be just sitting here, and you can see these 4 jumper pin connections, so they will go to the microcontroller separately. So there will be nothing mounted here except the parts which we will need to drive the CCD. Some resistors, capacitors, a very precise reference voltage, and a operation amplifier to invert the signal. So that's all. So I will assemble 2 boards because I need another board for another further project. So I will prepare the stuff for that, and then I return to you with another camera view, so you will get everything in a close-up perspective. So before applying the paste, I just want to share my, let's say, secret here, but I already mentioned this in a previous video, that whenever I put the parts on a board, I'm already cheating a little bit. So when I show you the shot when I place the parts there, it might look fast because I have already prepared. So on these 2 boards here, I have already set up the parts. I put them to their corresponding places, which means that whenever I lift them, I know where they come from and I know where I have to put them. So I can, in reality, I can work quite fast and pick and place the things with quite good, let's say, precision and accuracy, because I see the parts. So I don't have to open the bags one by one or pick them from a box where they can be aligned in a funny way. For example, you pick up the capacitor in the wrong way or the voltage reference in the wrong way. That can happen when you just pour everything in a box. But here I put everything on a board, and then I just use it as a donor, and I just pick the part and put it on the board which I want to use. So I will follow that strategy here as well. But before placing the parts, of course, we need to apply a little bit of solder. So I will use these 2 guys on the top and the bottom as a support, and then I will just put this over here. Of course, I will align the tabs with the holes, and then I just slide it with a spatula, but of course I show it to you. So let's see how the solder is being applied. So as you can see, everywhere the solder was applied properly. I'm satisfied with it. So yeah, let's just put the part there where they belong. So the parts are in place, so let's solder it. So the soldering part is done regarding the SMD parts. So now I'm going to move to the other side and hand solder these parts, which are the mounting parts, the sockets for the TCD1304 CCD. So let's do that. So it is done. I have put everything together and I screwed on the, let's say, back plate on this spectrometer. And what we have here, obviously I have 8 cables. 7 out of these 8 is functional because there are 2 grounds. The reason for that is because I did not want to have the number of connections here. So there's a 2x4 header here. Or maybe it's easier if I show it like this, that guy there. And 2 connections are ground. But actually I can use it in a smart way that one ground will be just plugged into a microcontroller, but then the other ground I will twist it around the signal pin, which carries the output signal from the CCD, and that hopefully will remove some noise or get rid of some noisy signals. We will see. So here I have to admit that I did a mistake, and the mistake is in the distance in between these 2 holes. Apparently I made a measurement mistake somewhere, and they are closer together than they should be. So I had to grind a little bit out of these holes. So they are in this board a bit oval shaped towards the edges of the board. So I will redesign this board in a sense that I will just put the holes where they belong. I triple checked everything, but seems like it was late night when I sent this, and yeah, I did this mistake. It happens, but that doesn't destroy any of the functionalities. I just had to grind it with some grinding equipment a little bit. So I extended the holes a little bit, so nothing extraordinary. So then inside you should see the CCD, this guy here. And once again, how this spectrometer works is that here you can connect an optical cable with an, I think it's called SMA connector. And then inside this block there is a slit. I don't remember its size, but there is a slit. So then we go on this collimator or collimating mirror, which creates parallel rays of the incoming rays. And then parallel rays are being reflected on this diffraction grating. This is again 1800 grooves per millimeter, and the blazing angle or the blazing wavelength of this thing is 500 nanometers. So then from this diffraction grating, the diffraction happens and the split up light is scattered towards this focusing mirror. So then this focusing mirror focuses the beam, or now individual rays, towards the CCD, and then they will end up somewhere on the CCD. And then we capture these individual rays. And how the calibration goes on is basically, I explained it in the previous video, but we expose the CCD to known wavelength lights, possibly with a laser, because that is a coherent light with a well-defined wavelength. So that goes in, and then there will be a peak intensity on the CCD somewhere. So we can say that that peak at the 725th pixel belongs to the red light at 650 nanometers or something like that. And then we note that down and we repeat this experiment with different wavelengths, and then we will have a set of points. We fit a slope on that set of points, and from that equation and the parameters A and B, we can substitute any pixel value and get the wavelengths from that. So I have this red laser here, and this is the 650 nanometer laser, and I will point the laser, as you can see, against the slit here, and then I will try to see if we will see the spot somewhere on the CCD. And I can see it. it's at the very edge of the CCD. I turn off the lights and hopefully you will see it as well. So lights are off, and there you see the red dot, or that's actually a line which is the same shape as the slit, a horizontal line. So that's the very edge of the CCD. And then a green laser, which is at 532 nanometers. So then the spots should travel around that direction. So there should be a green spot somewhere around here. And there you see it in the center of the CCD. So this is how it works. So now I will move to my computer. First of all, I will show you my new software for this capturing, let's say, system. So I renewed my CCD capturing software on Windows, and I will show you how it works. I will just move my finger in front of the CCD, and then I will shine these lasers through this port and slit, and we will see how the peaks look like. So let's go to my computer and continue the experiments there. So here we are in front of my computer. We are looking at Microsoft Visual Studio and some chunk of my code. So I will start the code, and that should open up the window, which is right here. So it's a very simple interface. I added some grids, so it looks better. Now the integration time actually works, and I have an averaging mode as well. So I just keep collecting and summing each individual pixels, and then I always average it by the number of exposures. And I can also save the data into a file. It is just saved in 3648 columns, line by line. So whenever a new line comes in, which is the full information of the CCD, that will be saved as a new line with 3648 columns in a TXT file. But that's not important now, so let's look at the graph. So I just connect to my microcontroller, and then I select an arbitrary integration time, let's say 50 microseconds, that should work. And then I just start collecting the samples by clicking here. So now you can see that the signal here is quite high. We have a 12-bit AD converter, so the highest signal should be around 4096 if I'm not wrong. This is now 3500. And here in the beginning we have the dummy pixels, and this is now just basically a homogeneous light. So I will put a pen in front of the CCD, try to put it in front of the center, and let's see what happens. So there it is. And now I move it left and right, and you can see that it moves in real time. So I can capture the CCD, plot it here, as you can see, with a very little noise, and it moves in basically real time. And now I have the pen actually inside this optical box. So I have to be careful not to touch any of the optical elements like the mirrors or the grating. But you can see that I can move left and right. I will try to locate some thinner objects in front of me. I'm sitting by the computer, so there's a thinner object here, as you can see. So we can actually measure thickness with this if we want. Some even thinner object, if I can get it. So you can see that this is just a piece of a jumper wire, and then I'm moving in front of the CCD, as you can see. And yeah, basically that's all. So now I remove the light sources a little bit around me, and I will shine the laser through the optical system, and we should see what happens. So now I remove the light sources in my room a little bit. So we still have some background light, but I can further decrease this. As you can see now, it's very little. And I can even further decrease this. So now we barely have any light. And now I will shine, or try to shine, the red laser through the slit. And you see the peak at 3500 pixels, somewhere there. So you can see that it's a very consistent peak. Sometimes I don't shine the light through the slit straight, so then you see that now the peak is very broad, but that's just because the incoming light is not so good. But you can see that I can create a peak like this as well. So with this value, if I would fit this peak and find the center of it, I could say that the light, which is 650 nanometers wavelength, is at around 3600, let's say, pixel. And then I also have a green laser next to me. So let's see what that does. That should be somewhere at the center. There you go, very nice narrow peak. So I nailed to shoot at the slit very nicely. So then I can say that at around 1400, I have the green peak. So with these 2 points, I could have any kind of arbitrary light source. And based on the number of available pixels on the CCD, plus the incoming light's frequency or wavelength, I could guess what is causing the, for example, absorption or things like that. So yeah, I switch back the lights a little bit, at least, so I can see. And yeah, now you can see that one thing is that I improved my CCD software. So you can see that this plotter now works amazingly, and a lot of frame is captured within 1 second. Actually, you can see the counter here, and each time roughly 17.5 frames come per second. So that's the frame rate, 17.5 frames per second, or hertz, however you want to define it. And I could make this faster as well, but I found this perfectly fine for me, for my task, and it's just enough. So this is how it works. You could see that it works properly. I will put some pictures of my setup as well, and this test setup, which I'm like running now, will be also included somewhere. So you can see that everything works nicely. So I think I finished the video here because I showed everything what I wanted. First of all, I made this new PCB. I have to improve it because I messed up the dimensions of the holes, but that's a very tiny thing to improve, so I will fix that within a few weeks probably. And then I will do some experiments, so I will try to find some light sources and some other things, and I will try to make this spectrometer into some kind of interesting instrument. Of course, spectroscopy is a very interesting topic, so I think there is a lot of potential in that, but I will try to make it interesting within my, let's say, skills and capabilities. And then, of course, I have other projects with this CCD, which is also maybe more interesting than this spectroscopy, so stay tuned. So if you are interested in this PCB, please check the link in the description or on my website, and you will go to pcbway.com and you will be able to order this exact PCB. And it's very good because then you can mount this on an even smaller place, and also you can drive the CCD with this. I think it's a very useful circuit. And also all the resources are shared on my website, so please look around there because I showed you how to drive this CCD and so on. And please stay tuned because I have other projects, as I said, and that will be very interesting. So I hope that you learned something from this video. I hope you found it entertaining, and see you in the next video.